In this video, we're going to turn to transcription in eukaryotes now. And we're just going to start by talking about RNA polymerases again. And eukaryotes use three RNA polymerases to carry out DNA-directed synthesis. And we call these RNA polymerase 1, 2, and 3. So 1 is in the nucleoli, and that's going to make your rRNA. 2 is in the nucleoplasm, which will make your mRNAs. 3 is also in the nucleoplasm. That's going to make your 5S RNA, tRNAs, and a bunch of other small nuclear and cytosolic RNAs. In addition to these three, mitochondria and chloroplasts will have their own RNAPs. And these RNAPs can be good targets for antibodies and other drugs, which makes sense, right? So let's say that you have a bacterial infection, you want to kill the bacteria. Well, a bacteria can't live without protein, so if you stop the RNA polymerase, then you stop the bacteria from working. So if we know what the mammalian RNA polymerases look like and the bacteria RNA polymerases look like, we can design drugs that target one and not the other. So we're going to look at RNA polymerase 2, for example, on our eukaryotic RNA polymerases. And these are huge complexes, and they are a lot more complex than the prokaryotic versions. However, if we just look at it, it looks like the crab claw RNA polymerase we were talking about, the prokaryotes. So that's what this TTH and TAC means. Those are the prokaryotic RNA polymerases. Now, RNAP2, we have two magnesiums that are right near 5 conserved acidic or negatively charged residue. And this tells us that we're going to have a mechanism similar to what we saw in our DNA polymerase. Now, the surface of this protein, mostly negative, except where we bind the DNA, which is positive. And we talked about this when we were talking about the prokaryotic RNA polymerase as well. But these negative charges will probably direct the DNA to the positive charges where DNA will bind, and we can start our mechanism. Now, if we look at the C-terminus domain of RNA polymerase 2, we will see that there are 52 repeats of the amino acids PTS, PS, YS. These SARE are subjected to phosphorylation by C-terminal domain kinases and phosphatases. And this phosphorylation and dephosphorylation is very important because transcription will be initiated when the C-terminal domain does not have any phosphates. But it will only start to elongate after phosphorylation. So these serines in the C-terminal domain are serving as a control point for the processes of initiation and elongation. Right, so let's look at the elongation complex now. So when the RNA nucleotide polymerase has both DNA and RNA bound, our RPB2 subunit, which is the cyan subunit, swings in and closes across the DNA. So the DNA can't leave the RNA polymerase. We can still move along the DNA, but we can't dissociate from the DNA. So this is why in experiments we see this enzyme more or less has infinite processivity. It'll never fall off until given the command to do so. All right, so let's look at our polymerase now and look at some of the different parts. So we have a part of the protein called the wall. And what the wall is doing is that it's directing our DNA to leave at roughly a 90-degree angle. So our DNA is coming in and then it's being directed to leave. Near this wall, we also have a base that will be pointed at the active site towards our floor. And this will be read by the polymerase. And it's also going to be paired with the 3' end of RNA. Now, when we are interacting, that is when the polymerase is interacting with the DNA and the RNA, that's all going to be through backbone interactions, which again makes sense we're going to read all types of genes with this protein, so we can't be nucleotide specific, but we can be specific to what's in all DNA and RNAs, and that's the backbone. What's really cool about this is that we can tell the difference between RNA and DNA. Remember, the only difference between RNA and DNA is a 2' hydroxyl. RNA has it, DNA doesn't. So we want to only incorporate RNA into our growing structure, so RNA polymerase 2 can tell that. Now we also have a rudder up here, so when we're making RNA and DNA, we're going to make the RNA-DNA complex, but this rudder is going to separate the RNA from the DNA. This allows your DNA to reform into the double helix, and it's allowing your RNA to come off as well. We have a bridge sequence down here, so we're going to contact the DNA at I+1. That is one site upstream to where we're currently doing synthesis. Now, the way that this bridge is bent, it'll push the I+1 to the I-1 spot, leaving the I+1 for the next nucleotide to come in and do the next reaction. And since our new nucleotide comes into the I+1 position, our DNA cannot move backwards. If a nucleotide didn't come in, you could think what we just pushed to the I-1 could go right back to the I+1. But since a new nucleotide is there, we are preventing any movement from going backwards. So let's look at our RNA polymerase again in a different type of representation. And really, the way we can tell which nucleotide to incorporate is a two-step process. So we have two different sites, E and A. So in the entry site, we're just going to bind any nucleotide. We don't care what it is. If there are nucleotides floating around, it's going to be trapped to our entry site. Once it's in the entry site, we're going to pivot that nucleotide to the addition site. However, that pivot is only going to happen if our nucleotide forms Watson-Crick base pairs. So let's look at this zoomed in image. So our blue is our template, our greens are non-template. Red here is the RNA we have made. Blue here is at the entry site, orange is at the addition site. So see, we have a nucleotide bond here. And what that can do is that can flip over to the entry or the addition site, and if we make a Watson-Crick base pair, we can connect to our RNA. The way we know if a base pair is made is through this trigger loop. So that's in cyan here. So this trigger loop is behind or underneath a correctly base paired nucleotide with the DNA. Then you're going to form a hydrogen bond network. And this hydrogen bond network is what is your safety mechanism to say, do not attach an RNA unless this trigger loop has an excessive hydrogen bond network, because then you can have a conformational change and you're going to add your new nucleotides. And it's with this hydrogen bond network that allows us to discriminate between DNA and RNA, because if a DNA trinucleotide came in here, we would not form this hydrogen bond network, so we would not add to our growing chain. And that's it for this video. I will see you in the next video.